Hi there. Let's work on Unit 5. We're beginning Unit 5 today. It will start with Lesson 5.1. As you can see by the screen in front of me, we are going to be working with the mean value theorem today. So this is a biggie. There are about 4 really large theorems in the AP Calculus AB1, and we have discovered a couple of them already. We've worked with the intermediate value theorem. We're coming in with the mean value theorem. In this unit, we also pick up the EVT, the extreme value theorem, and then when we get to Unit 6, I bet we'll pick up our last one. So let's move forward. So just a little comparison or a little bit of review about average rate of change versus instantaneous rate of change. And there's a point to this problem as we move through it. So here we go. Average rate of change, we all recognize that average rate of change is really just a calculation of the general slope formula, right? Where we work off the endpoints. So we have f of b minus f of a, that's our two y values, taken over the difference between the two x values, b minus a. So if I had to calculate the average rate of change for this particular problem, let me move things just a bit. I would say that my average rate of change was equal to f, here's my interval, 5 minus f of 1 over 5 minus 1. And plugging that in, trust me, you're going to get 10 minus 2 over 4. And that is 8 over 4 is a 2. Coming over to the right side, let's talk about instantaneous rate of change. Given f of x over the interval a to b, the IROC of f of x at x equals c is the derivative, right? Instantaneous rate of change, we correlate that with a derivative. Find the instantaneous rate of change of f of x. Well, to do that, I have to refer back up here to f of x. So I'm going to get f prime of x equals 2x minus 4. And that is IROC, isn't it? Now, that next box says, is there a value of x where the instantaneous rate of change equals the average rate of change of f of x over the interval 1 to 5? They want instantaneous rate of change equaling average rate of change. I'm just going to document that's what I want to do. IROC equals AROC. Is there a place that happens? Oh, no. But let's check it out. We know what IROC stands for. That's f prime of x. And AROC was what we did up above, f of 5 minus f of 1 over 5 minus 1. Now, f prime, we calculated that out in that previous box, 2x minus 4. So I'm going to substitute that for f prime. And we did our calculation for AROC. That turned out to be 2. And it sure looks like it exists, doesn't it? We can solve this quite easily. It looks like x of 3, AROC and IROC would be equal. So let's go look at the graph. We knew we were working with, well, let's go back up and look at f of x. Definitely a parabola that was opening upwards. So we see that in the black curve graphed out for us. We did our calculation and came in with a 2. So this blue dashed line represents AROC, right? The slope of this line is our average rate of change. And then if I go along the red line, this is my IROC. And if these two equal, we should see parallel lines, right? If AROC equals IROC, I should have parallel lines. That is not the correct spelling. Sorry about that. For parallel. Where was I going with that one? All right, so parallel, double L, E L. Parallel lines should exist if it's the case that we have AROC equal IROC. So this is the foundation for the mean value theorem. So down below, in the example above, we were able to find a value in the given interval where AROC equaled IROC. And it's natural to wonder, if this is always the case, can we always find a place where f prime equals the average rate of change in a given interval? This forms the foundation of the mean value theorem. The mean value theorem is what we refer to as an existence theorem, meaning it's going to guarantee that it exists under certain conditions, but not necessarily how to find the point, like we were able to find 3. Well, this theorem doesn't actually find it for us. We'll have to do that, a little bit more work to do that. This type of theorem is important in mathematics as they guarantee that a value exists. Okay, so that existence idea, that the value exists. All right, let's move on. Example 1, you may want a ruler for this problem. So go grab a ruler, hit pause, go grab a ruler. Now what we're going to do is we're going to draw some lines, thus the ruler. So it says, for each of the functions below, draw a line segment between the indicated points on the graph. And I can't read because I'm sitting over top of it. Is there a point on the graph where the indicated points, where the slope of the line tangent to the point is equal to the slope between the given points? If so, draw the line. All right, so let's connect up the endpoints there. That's our A rock. Oops, still drawing lines. Oh, still drawing lines. This is our A rock connecting the points. It's also known as a secant line. Then, is there another point? So now you have to do your best to imagine a parallel line. Can we draw a line parallel? I'm kind of thinking right about here. This is my point that I'm interested in. Some x value of c, right? Dotting down so you can see. There's c. And this is my I rock, the tangent line at the point of x equals c. Looks like it's between the values of 4 and 5. So yay, it exists. Yes, we could do it here, right? Do the same thing. Let's go to the next problem. Connect your segments up, or your endpoints with a segment. Got it. That's our A rock. If you want to draw it right in that this is A rock. Now, is there another spot? Can I find a point where I can draw in a line parallel to A rock? So I have I rock equals A rock. Well, sharp points, we know derivatives don't exist on sharp points. So no, I can't draw it there. I wanted to so bad. I can't draw it there, I can't draw it there, can't draw it there. And the rest of these line segments are linear segments, and they already have a defined slope that's not matching A rock. So I have to say no, we can't, right? These particular points right here, I'm trying to think of what I'm going to do here. I'm going to just show this. Not differentiable there. See if you can spell differentiable. Not differentiable at sharp points, just to drive home how we figure that out. So nope, can't get an A rock equal I rock on that one. Next problem, let's snap in. Oh, that purple's pretty. Snap in our secant line. This is it's my A rock. Uh-oh. It's my A rock. What the heck? Draw. This is my A rock. And now, imagine, is there a point? Can you find that point? I want you to find the point that the tangent line exists that has the slope parallel to the A rock, and then go do the other one. I'm going to hit pause, and I'll come back with the answer. Okay, so here's what I came up with. I got my A rock line in. I've got my I rock line in on that example on the left. There was definitely a point I could find that that they exist, that they have parallel slopes. But the second example on the right there, I couldn't find a spot, right? So I had a yes, it's happening, and a no. Now, What conditions, in the examples above, which graphs were you able to find a point between the indicated points where AROC and IROC were equal? Under which circumstances do you think we can guarantee a point that this exists? What we're trying to do is figure out what is the hypothesis of our theorem, our mean value theorem. Well, this one, it was a nice continuous function and it was differentiable, no sharp points, right? The function on the right, ooh, it wasn't continuous, not continuous, and we couldn't find an IROC spot. The other two, ooh, love this. This is a very nice continuous and no sharp points, so continuous and differentiable function. So much abbreviating, but you'll get the hint. And that turned out, yes, we could find AROC equal to IROC. The other one, not differentiable. It was continuous, but it wasn't differentiable. So I think we've kind of got a pretty good idea of what it takes to guarantee that AROC equals IROC. And the examples, under what conditions do we get this guarantee happening? The circumstances. We need a continuous and differentiable function, it appears. In order to guarantee AROC equals IROC. As I was writing this down, I was thinking continuous and differentiable function on, a certain interval. It doesn't have to be everywhere, but that interval that we're interested in. So I'm going to add that. Okay, we've got the general gist of this, and let's go into the mean value theorem. If f is continuous on the closed interval a to b and differentiable, so notice how both things are mentioned in the open interval a to b, then there exists, we said it's an existence theorem, a value x equals c in a to b, so c sits between a and b, right, such that f prime of c equals f of b minus f of a. What does f prime of c represent? That represents IROC. F of b minus f of a over b minus a, that represents AROC. The mean value theorem has some big ideas. The function must be continuous and differentiable. Write it fully out if you don't think you'll be able to remember what CONT stands for, or if you want to use differentiable, DIFF apostrophe T, that'll be fine. Mean value theorem guarantees that IROC equals AROC somewhere in the interval. MVT is an existence theorem. It guarantees something will occur, but it doesn't tell us exactly where it occurs. We will approach MVT problems in a similar way that we did the IVTs. We've got to check those conditions. Remember, the conditions are a simpler way to write, check the hypothesis of the theorem. And we'll use the endpoints, we'll state conclusions. So just a little reminder about what intermediate value theorem was, because it's very easy to get intermediate value theorem confused with mean value theorem. If f is continuous, notice it doesn't have to be differentiable. On the closed interval, there's some y value of k that sits between f of a and f of b, or a y1 and a y2 value, right? That k sits between them. And we talked about this betweenness idea because it could be one way or the other. I don't know which is larger, y1 or y2. It could be either way, but k sits between them. There's at least one number c in a to b such that when I plug in c into my function, I get out k. And that's the intermediate value theorem. We had to have continuity. So if I had the number 1 there, the number 5 there, and I said, if k equals 4, then is there a c value that when I plug in f of c, I get out 4, such that c sits between, what should we call this? Let's use different numbers, 2 and 6, such that c sits between 2 and 6. And if it's continuous, absolutely, where would be 4? About there. So There's 4, and voila, we found C, and it's between 2 and 6. On the back side, IVT versus MVT. You can see that you have to read them really carefully. You noticed my mistake. I was thinking velocity on that one instead of acceleration, and that was the difference between going IVT versus MVT. So, intermediate value theorem. What conditions must be met? It must be continuous. Continuous function. And you have to have that betweenness. And K between F of A and F of B. We can't order them because we don't know the values on those. Whereas the mean value theorem needs continuity. So I'm going to write continuous and differentiable. Needs both. It's a little bit more difficult to apply the MVT. What to look for? Conclusions about the usually you're looking for your conclusion is that there is a value between, I'm going to say a y value between the y values presented in the table. Presented in the table. Okay. On the mean value theorem, our conclusion is the IROC equals the AROC. And by that we mean F prime of, sometimes they say C, F prime of C is equal to F of B minus F of A over B minus A. All right. So this example, we're given velocity, aren't we? We got the velocity function, the time. A bug is moving along the x-axis, the velocity is differentiable, cool, which means it's also continuous, and selected values are given in the table above. Is there a time C on the 0 to 9 endpoints, or that interval, such that V of C equals -1? So V of C, we've given V, all we're trying to do is decide if -1 would be between those Y values. And indeed, it does look like -1 would fall between those, right? So our work would be V of T is differentiable. These are things that you would have to state on your AP exam if you were doing these. From that, well, what did we say the condition was? We had to have continuity. So V of T is continuous because it is differentiable. And I need to know that -1 resides between F of, which one do I want? F of 9 and F of 0. Or I could even make it more obvious by using those numbers. Okay, and it wasn't F. Let me clear that up. It was V. So picky, aren't we? V of 9, V of 0. Good. So since we have continuity and betweenness, then we can state since V of T is continuous on 0 to 9, I think it was 0 to 9, right? The IVT guarantees that there is a time T on 0 to 9 such that V of T equals -1. That would be our conclusion. So this little statement here, it's almost like, think of quote marks around this. This is a statement that you could recycle over and over, right? Kind of fill in the blank style. All right, let's go back over to this other one, do the next example. We knew that mean value theorem requires continuity and differentiability. What we're trying to prove is that AROC and IROC are equal. So they give us the table. It's a V of t table again. A bug is moving along the x-axis. The bug's velocity is differentiable. Awesome. And selected values are given in the table. Is there a time c between 0 and 9 such that a of c equals -1? All right, I am reading way more careful this time. They're asking about acceleration. The table has velocity. This is MVT all the way. So what does it take for MVT? We got to show our work, and that work is going to be the fact that we start out with V. V of t is differentiable because it was given, and V of t is continuous because differentiability implies continuity. And therefore, f prime of c will equal f of 9 minus, that's a 9, not an a, f, here I go with the f's again, and it really is v's, isn't it? Glad I caught myself. V prime of c equals v of 9 minus v of 0 over 9 minus 0, or over 9. I'm going to make it obvious, 9 minus 0. Whew. Let's get our derivative down. Oh, we can't, because all they did is, I could say a of c if I wanted there, which is equal to v prime. The statement, since v of t is continuous and differentiable, I know they only gave us one blank, but I'm going to include both differentiable and continuous on our 0 to 9, and oh, continuous here. Sorry. Remove that on 0 to 9. They did give us two blanks. The MVT guarantees that A of C equals V of 9 minus V of 0 over 9 minus 0. Off of the table, we could even take this one step further. 9 is -4, and -4, and dang it, I forgot it already. 0 turns out to be 5. Dang it. There we go. Over 9. And you can go further if you want. Might as well. It's -1, isn't it? So we're trying to show that the acceleration equals -1. Whew. I think I'm going to stop because I think this is getting long, and then I'll finish up examples 3, 4, 5, 6 on the other video.